and I did this in 30 minutes the first time, and now I'm going to have to do it in 5. This is the entire internet in 5 minutes. First, the caveats. I am not a network engineer. I write terrible Python and JavaScript for a public radio station, and much of what I do here is probably apocryphal and possibly wrong. Please don't rely on this information for anything important or you might catch on fire. Good, now let's get started. What happens when you load a URL? This is what we're going to do. We're going to trace a request through a website as it happens, but first we need to cover some basics. A client is a computer that makes requests. A server is a computer that responds to requests, and the internet is a global network of physically connected servers and clients. And finally, the World Wide Web is a subset of the internet concerned with hypertext links between resources which are URLs. Got it? Good. Now it's time to get down to business. We're going to cover 4 really big buckets: networking, DNS, routing, and HTTP. The first one we're going to cover is networking. Networking relies on the 7 OSI layers for communication. These are the fundamental building blocks that underlie all the interaction between your computing devices and other computing devices. It's what separates us from the animals, really. The problem with OSI is that it's kind of complicated, and frankly, it's pretty hellish. So be prepared to abandon hope. It's not really that bad, but preserve your presumably fragile mental state after interspersed images of cute kittens throughout the section of the talk. There are 7 OSI layers: the physical, data link, network, transport, session, presentation, and application layer. Every one of these communication travels up the stack from the lowest level to the highest, and that means that there are going to be means of communicating between the levels. The first level we're going to talk about is the physical layer. It is the translation of communication requests from hardware-specific operations like radios or cables and whatnot to something else. This is a cat. Ethernet, Bluetooth, USB, 802.11b, like Wi-Fi, among other things, happen at this layer. All of the unreliability gets smoothed out the next level up in the data link layer. This is a theme throughout the OSI layers. All the rough spots at the lower layer are resolved through the next layer up. There aren't a lot of fun technologies working at this layer: packet switching, DOCSIS, pretty cats. Quality of service, and VLANs. The good news is that everything is switched from bits to frames. That makes everything more reliable. Now, we're going to lose reliability at the next layer, level 3, the network layer, but this is the responsibility of packet forwarding, including routing and IPv4 and IPv6. So, there's another cat, and at the very next layer, we're going to start talking about packets. The good news is that packets are the atomic unit of the internet, and that means that other data formats like frames, bits, etc., and the internet protocol is all about packets. It's a layer cake of messages, including headers that identify a bunch of things and other stuff. I realized that this layer had no kittens, so I'm going to move on to the next one. The next layer we're moving to is layer 4, the transport layer. Between this layer, we are concerned with the orderly reliability of delivery between packets between points on a network. This is where we speak TCP and UDP, which are the primary languages the computers on the internet speak to each other, and also kittens. Moving on to layer 5, the session layer. This layer is concerned with the opening, closing, and managing of sessions, which are semi-permanent dialogue between applications. Now we're going to move on to layer 6, which is the presentation layer. It's concerned with encryption and decryption. You should talk to Jeff Larson about that. There's an awful lot of boring things that happen in layer 6, like Telnet. Now, the final layer of the OSI layer is layer 7. This is known as the application layer, which is where we're translating lower-level data formations to formats that are human recognizable, like basically text. The only reason we're even talking about the OSI layers is because I would like to talk to you about HTTP and things like DNS. DNS is the domain name service, which is the internet's gigantic phone book for translating things like URLs into IP addresses. So when you put npr.org in your web browser and get 216.35.221.77, that makes computers happen. The way we do this is through A records. These translate things like that into something else. Now, who holds all the records? Computers like this one. This is the kroot server at krootservers.net. There are an awful lot of them. They go A through M. One of them is even hosted at the University of Maryland, which is pretty awesome. Now, you're going to notice that the rest of these servers are throughout the United States and also throughout the rest of the globe. The internet is obscenely physical. We're going to talk about that a little bit later. Now, if you use a Unix tool like dig.npr.org, you're going to see the information about NPR, and you're also going to see that this is an internal DNS server that is talking to our computer. Why is it an internal DNS server? Because there are layers and layers and layers and layers and layers of cache until you get to a root name server. This is why it takes so damn long for your domain name to propagate. Now, if you want to look at what npr.org actually is, it is a record like this. It is updated by someone named Lily Ladd, who is very nice, and it was updated first time on the 13th of December 1993. The top-level domains are created by registrars. They submit A records to their DNS servers, and that is how you own a domain name. But if you own it, how do people get to it? That's what routing is all about. Routing is what IP addresses move IP addresses between computers. There's a finite number of them, and every device connected to the internet has to have one. There are 4.29 billion IPv4 addresses, and IPv6, there are that many. It's 348 billion something else. But we can assign an IPv6 address to every atom on the surface of the Earth and have enough addresses for another 100-ish Earths. Well, what's an IP address? It's a dotted quad. It looks like this. With some exceptions, there are some private non-routable IP addresses, but we're not going to talk about those. These are those ranges, and they're for using little mini internets. The actual internet is called a WAN, not a LAN, and so that's a wide area network. Did you know that Xerox owns 16.8 million addresses in 1994? Also, Apple owns that many, and also Ford Motors, and also Prudential, and the DoD has 10 blocks of 16.8 million addresses each. That's why we're running out of IP addresses. That's this group's problem. They're called ICANN. They have links of IP addresses between each other via things called routes. The internet is really physical. If you trace route npr.org, you will see a long thing like this. The first 11 hops are just getting out of Amazon's data center in Portland, which is where the server I rented was hosted. If you look at these, it moves us between Portland and Seattle, Seattle to San Jose. We're also going to change ISPs 3 times. When we change ISPs, it's called peering. These last 3 things that we do get us across from San Jose to San Francisco, where the NSA looks at our information. Then we go from San Francisco to New York City. Wait, what? Look at all this United States that we travel across. That's the internet. And CenturyLink is part of the internet backbone. They get 20% of the traffic to the internet. They have 2 10-gigabit pipes between New York City and San Jose, and it's not nearly enough because they have 15 15 of them between Chicago and New York City. Back to the story. This is the last handful of hops. They're hopping us between New York City and our hosting facility in Northern Virginia. That's the map again. The summary, 2 of those hops get us 3,100 miles. The other one's only 1,000. HTTP, it's the last bit. I want to show you a slide of Tim Berners-Lee. He's famous. He has a lot of titles. Like a stone cold elemental badass. Hypertext language, which allows us to have links between things. He invented that www that goes in front of stuff. He wrote the first web server. He invented the HTTP / notation, which he later recanted on. He also invented a way for us to connect TCP/IP, DNS, and hypertext to a request response protocol. I did not get this all done, and I'm not even going to try going into Ben Welsh's time because he's much better than me. But you can finish the slides on the web, and there's the last one. Oh no! This HTTP status wrappers. Oh, talk to Jeff Larson about SSL. Oh, there we go, I'm done. But that's what it's like.